Hi, welcome to the video on speed control of three-phase induction motor. As we know that a three-phase induction motor is practically a constant speed motor like a DC shunt motor. But the speed of DC shunt motor can be varied smoothly by using simple rheostats. This maintains the speed regulation efficiency in DC motor. But in three-phase induction motor, it is very difficult to achieve smooth speed control. So if the speed control is achieved by some means, the performance of the induction motor in terms of power factor efficiency will get adversely affected. So for that, we know the torque equation. Torque is proportional to S into E2 square R2 and divided by R2 square by R2 square plus S into X2 whole square. So using the torque relation, we can see that speed can be controlled either by changing by the synchronous speed or by changing the slip. Similarly, torque produced in case of three-phase induction motor is given by N is equal to Ns into 1 minus S. That means I can change the speed of the rotor by changing Ns value or by changing the slip. So Ns value means we have to talk about stator side, and if I have to change the slip, then we have to think of rotor side. So from the both the side, we have a methods to control the speed of an induction motor. So as I in this slide you can see the stator side, if we have to control the speed, that is Ns is equal to 120 F by P. If you observe, I can see that frequency can be changed and supply voltage control and controlling number of stator poles to control Ns. So we don't normally discuss controlling number of stator poles to control Ns, but we do discuss about supply frequency control and supply voltage control. So from rotor side, we have the three methods: adding external resistance in the rotor circuit and cascade control, and injecting slip frequency voltage into the rotor circuit. So we don't discuss these two, but we do discuss adding external resistance in the rotor circuit as per the syllabus. But in the stator side, I have left one more method, that is adding rheostat into the stator winding. So that is also one method where we can control the speed using that. So coming to the rotor side, speed control of three-phase induction motor, we have the supply frequency control or V by F control. As you know that the synchronous speed is given by 120 F by PS. So F can vary the speed Ns. In that case, if you vary F, the frequency, very important, the air gap flux which is present in the motor will also adversely affected. So we all know the transformer equation, E is equal to 4.44 phi m n1, okay, into F. So if you look at this transformer equation and relate it to this, I will introduce K1, which is a constant of the stator winding, and T phase is turn per phase in the stator. So V is equal to 4. If you take this entire denominator to the left side, V is equal to 4.44 K 1 T phi F into phi G. So as I said, if you change the frequency alone in the stator, it will have an adverse effect on this air gap flux. That means this air gap flux increases with the increase in the frequency. So or decrease in the frequency. So if you decrease the frequency, this this goes increasing, and this magnetizes will increase the current, that is sharp current will be produced in the rotor, which will have a effect. So in that case, we need to maintain this phi G, that is the air gap flux constant throughout, irrespective we change the frequency. So we cannot alone change the frequency, then we have to change the other variable which is in this, as per the equation, is only voltage. So that means we have to change the V by F ratio in such a way that this phi G remains constant, and this will not cause any current, very high sharp increase in current in the rotor. So for that, initially we need to convert this constant voltage and constant frequency of the AC, which is given to the stator side, to a converter, where this converter converts to DC, and then it is converted to variable voltage and variable frequency using this inverter model, with built-in model, where we have to maintain this V by F in a ratio in such a way that the stator will be given with change in the frequency, where we can have a control over the speed. So from this expression, if the frequency F is changed, the value of air gap flux is also get affected. So as I said, it not only increases with the current, it results in the losses also. So it is very important to maintain this 5G constant. So for that, we have this type of arrangements made normally for the speed control, and it is widely used in many industries, that is free supply frequency control or V by F control method. So look at this. Normally, this is the torque speed characteristics at normal frequency. So when you increase the frequency, so F1 is greater than F, you can see the torque is increased and maximum torque is achieved even otherwise. And if you decrease the frequency is less than the supply frequency, then the torque will be less comparatively to this normal frequency torque speed characteristics. So we can increase and decrease above normal and below normal frequency of supply frequency in three-phase induction motor using this arrangement. The only disadvantage is that supply when obtained cannot be used to supply other devices which require constant voltage. So we should have individual scheme for separate motor is required, which is most costly. So speed control by supply voltage control. So supply voltage control, we know that torque relation, this if you observe here, we need to control this voltage. So we have to have a reduced voltage means we need to reduce this by having a only at this low slip region. So now E2, the rotor EMF at standstill depends on the supply voltage. So E2 is proportional to V. So also for low slip region, if you look at it, low slip region, this SX2 will be very less than R2. Therefore, this term is neglected. So in that case, torque is proportional to only S into P2. So if you reduce the supply voltage, then the torque also can be reduced, and therefore speed can be increased. So this is how speed torque control can be made from the stator side. So the third one is adding rheostat in the stator circuit. As I mentioned, adding rheostat into the stator, this is a stator. So we do add a rheostat between the stator winding and the supply. So by adding this, we can control and reduce the voltage of the supply and then given it to the stator. So we can have reduced voltage to the stator, thereby torque and speed can be controlled. So if you look at it, if the resistance is increased more than the normal value of R2 which is present in the R2, then the speed decreases with the increase in the torque here. Starting torque would be more. So this is the normal R2 with speed torque characteristics, and this is increased R2 speed torque characteristics where to come across. Thank you for watching.